Here I'm running a reaction in my backyard. This is sodium carbonate. I'm hoping you can read that label. I'll put some in the test tube. Now I'm rinsing my pipette. And now I'm ready to add some copper chloride. CuCl2, copper plus 2, chloride minus 1. You can see it's blue. I'm going to zoom in to give you a better view of the reaction. The frisbee's there to block the glare. Okay, copper chloride in my pipette. Copper chloride in my pipette. Sodium carbonate in the test tube. Here we go. Whoa, nice. Nice, nice, nice. Okay, I'll zoom in, see if I can get a close-up of that. So you can see the color's changed and it's become opaque. You can't see through it anymore. And those are signs of a chemical reaction. We've made some new compounds here. I don't have a centrifuge at home, so I'm just going to let this sit for a couple hours. So here's the results a couple hours later. This blue-green material is settled to the bottom. There's a clear layer on top. It looks really nice. I'm going to try to zoom in. There it is, beautiful.
Chemists have a notation they use to summarize what is going on in a chemical reaction like the one you just saw. This notation is called a chemical equation. Today, we will learn how to translate a chemical reaction written out in words into a chemical equation. This sentence here describes the reaction you just saw. Sodium carbonate and copper chloride react to form sodium chloride and copper carbonate. The first thing we have to do is translate these salt compound names into chemical formulas. So, our first salt is sodium carbonate. As you can see in this picture right here, carbonate ions have a -2 charge, sodium ions have a +1 charge, meaning we need 2 sodium ions for every 1 carbonate ion to make a neutral compound, to have the charges add up to 0. So, we can represent this here as a chemical formula by putting the positive ion first, so the sodium ion first, a little 2 indicating that we have 2 of them, then carbonate CO3 right here. Next up is copper chloride. Copper ions have a +2 charge, chloride ions have a -1 charge, meaning we need 2 chloride ions for every 1 copper ion to make a neutral compound. This means that this picture here is incomplete. I'm going to draw another chloride ion to make this picture complete to have a neutral compound. Okay, now we can write our chemical formula. Let's put the positive ion first, Cu, then the 2 chloride ions next, Cl2. Okay, so next up we have our products. First one is sodium chloride. So sodium ions have a +1 charge, chloride ions have a -1 charge, meaning we need 1 of each to make a neutral compound, making our formula NaCO. Finally, we have copper carbonate. Copper ions have a +2 charge, carbonate ions have a -2 charge. We need 1 of each, making our formula CuCO3. Now, are we done? No. There is a big problem with this chemical equation, and to illustrate what I mean, I'm going to recreate these compounds with the Lego models. I have recreated these compounds using the Lego models. This is sodium carbonate, copper chloride, sodium chloride, and copper carbonate. Sodium carbonate has 2 sodium ions for every 1 carbonate ion. Sodium chloride has 1 sodium ion for every 1 chloride ion. So, this is a problem because we went from 2 sodium ions to 1. And in real life, this cannot happen. We cannot have atoms just disappear off into nowhere. Mass is conserved. Matter cannot be created or destroyed. So, what I can't do to fix this problem is simply add another sodium ion like that, because it needs another negative ion to make a neutral compound. So what we can do instead is add another sodium chloride molecule. So now we have 2 sodium ions on the reactant side, 2 on the product side, 1 carbonate on the reactant side, 1 carbonate on the product side, 1 copper on the reactant side, 1 on the product side, 2 chloride ions on the reactant side, 2 on the product side. This equation is now balanced because we have the same number of each type of atom on both sides of the reaction. Okay, as you saw with the Legos, it turns out that we need 2 sodium chloride molecules to make this a balanced chemical equation. So to indicate this, I'm going to write a 2 right here in front of the formula for sodium chloride to indicate that we have 2 sodium chloride molecules. That number applies to all of the atoms in this formula. So since we only have 1 of each other molecule, we don't need to put a 1 right there. It's implied that it's 1 if you leave it blank. Okay, so last thing we gotta do is to indicate the phases of all these compounds. So to do that, we'll need our periodic tables, specifically turning to the back where it says solubility chart. Okay, so our first compound is sodium carbonate, and in our solubility chart, sodium is right here, carbonate is right there, and where they intersect, there is a Y. There is a Y. This means that this compound is soluble in water. It dissolves in water. So the proper phase label for it is aqueous, or AQ. AQ. Okay, next up is copper chloride. Copper is right here, chloride is right there, and there is a Y where they intersect, meaning that copper chloride is soluble in water. It dissolves in water, so the phase label is going to be aqueous, or AQ. Next up is sodium chloride. We should all be familiar with that. That's table salt. Sodium chloride is indeed soluble in water. It dissolves in water, so our phase is going to be AQ, for aqueous. Finally, we have copper carbonate. Copper is right here, carbonate is right there, and there is an N where they intersect. This means that copper carbonate is not soluble in water. It does not dissolve in water. This is that insoluble solid precipitate you saw in that chemical reaction. So I'm going to indicate it on this equation with an S for solid. Okay, now we have our complete balanced chemical equation with all the phase labels on it. Let's try another example. We have magnesium sulfate reacts with sodium phosphate to form magnesium phosphate and sodium sulfate. First thing we gotta do is convert these salt compound names into chemical formulas. So our first salt involved is magnesium sulfate, and to get the chemical formula, we'll first need to identify the charges of the ions involved using our periodic table. So magnesium is right here, number 12, and all elements in this column will form ions with a +2 charge. So let's write that down. Mg +2. Then sulfate is going to be on that chart in the back, the one that says solubility chart. So sulfate is right here, and it has a -2 charge. -2. So magnesium is +2, sulfate is -2. We're going to need one of each to form a neutral compound. So I can write the chemical formula from this. We have 1 Mg, 1 SO4. Our compound, our formula name is MgSO4. Okay, next up is sodium phosphate. Sodium is right here, number 11. All elements in this column will form ions with a +1 charge. Phosphate is on the back right here. Phosphate has a -3 charge. So, let's draw a picture. Phosphate has a -3 charge. Sodium has a +1 charge. This means we're going to need 3 sodium ions for every 1 phosphate ion to make a neutral compound. So I'm going to start with phosphate in the middle because we're going to surround it with sodiums. PO4 -3. Then we need 3 sodium ions, Na+, Na+, Na+. Okay, so we have a neutral compound, and we can write the formula from this. Put the positive ion first, Na, a little 3 to indicate that we have 3 of them, PO4 for 1 phosphate. Okay, so next up is magnesium phosphate. We know that magnesium has a +2 charge, so I'm going to write it right here, Mg +2. Phosphate has a -3 charge, so I'm going to write right here, PO4 -3. Okay, so we have an issue here. This is not a neutral compound. -3 + 2, they don't add up to 0. So we have an excess of negative charge right now. Let's try to add in some more positive charge by adding another Mg, another magnesium ion, Mg +2. So that didn't solve the problem. Now we have an excess of positive charge. So let's add another phosphate, PO4 -3. And we can resolve this issue right here by adding a third magnesium ion, Mg +2. So now with 3 magnesium ions and 2 phosphate ions, all the charges will add up to 0. This is a neutral compound. So our chemical formula is going to be Mg3 PO4. And if we have multiple polyatomic ions, we need to enclose the formula in parentheses and put a little 2 afterwards. So that 2 is going to apply to all of what's in the parentheses. Okay, lastly, we have sodium sulfate. We know that sodium ions have a +1 charge. Sulfate ions have a -2 charge. So we need 2 sodium ions for every 1 sulfate ion. So sulfate, SO4 -2. Sodium ions, Na+, Na+. Okay, then writing the formula, it is Na2, 2 sodium ions, and SO4, and there's only 1 sulfate ion. Okay, so I rewrote the formula names, so they're a little bit neater. So next thing up is to check if this is a balanced chemical equation, if we have the same number of each type of atom on both the reactants and product side. So on the reactant side, we have 1 magnesium. On the product side, we have 3 of them. This means that we need to add a 3 right here. So we have the same number of magnesiums. Then this 3 also applies to this sulfate, meaning we have 3 sulfates on the reactant side. We have 1 sulfate currently on the product side. So I need to add a 3 right here to have the same number of sulfates. Then let's see, on the reactant side, we have 3 sodiums. 6 on the product side. 3 times 2 is 6. So I need to add a 2 right here in front of sodium phosphate. So we have the same number of sodiums. Finally, this 2 applies to this phosphate right here. We have 2 phosphates right here. So now we have the same number of each type of atom on both the reactants and product side. This is a balanced equation. Okay, last thing we gotta do is to indicate the phases of these compounds involved. So first up is magnesium sulfate. Magnesium is right here. Sulfate is right there. There is a Y where they intersect, meaning that magnesium sulfate is soluble. It dissolves in water. The correct phase is going to be aqueous, or AQ for short. Next up is sodium phosphate. Sodium is right here. Phosphate is right there. There is a Y where they meet, meaning that sodium phosphate is soluble. It dissolves in water. Our phase is going to be AQ for aqueous. Next, we have magnesium phosphate. Magnesium is right here. Phosphate is right there. There is an N where they intersect. So this means that magnesium phosphate is not soluble. It does not dissolve in water. If you run this reaction, this will be your solid precipitate that forms. So I'm going to indicate that with an S for solid. Lastly, we have sodium sulfate. Sodium is right here. Sulfate is right there. There is a Y where they meet, meaning that sodium sulfate is soluble. It dissolves in water. The correct phase is going to be AQ for aqueous. Okay, now we have a balanced chemical equation with the correct phase labels. This is a powerful tool to summarize what goes on in a chemical reaction.